Hello developers, let's start developing. My name is Vekoslav and today we're gonna be taking on the 17th task of the Advent of Code 2023. I already looked into it and I am correct. We are back on the Gear Island and we need to do some things. We need to basically transport a crucible of lava, something like this, from one end of the city to the other. And each of these is a city block, and each city block needs to be transferred, and we need to minimize the lava loss, the heat loss, or whatever it was, as we get to this point. So, which means that we need to do some kind of mapping. But we have one significant obstacle that will make it harder for us. So we can move at most 3 blocks in a single direction before we must turn. Yeah. One of the issue is that we cannot go back, but generally when we're searching for the fastest path, we don't want to go back. If we don't want to go somewhere, we can just not go there. So yeah, for example, we have this path, which is the solution of this thing, and the heat loss is 102. And we need to take care of that. I actually did the input processing. It's totally trivial. We're just taking each digit and then we're mapping it out. That turns out correct, and that's quite fine. And we will need to do some pathfinding. So what do we need do if we need to actually find the actual path, the shortest path? So let's for a moment ignore these at most 3 blocks. Let's say we need to go from here to here. So one way to do that would be basically to do some kind of a node-based flat fill, so to say. So we can say that we are at position is 0, 0. And I will also create a new matrix. Nothing like that. It will have the size of the input dot length. I would fill it with 0 and map each item to a new array that has the input of 0 dot length, and I will actually fill it with number dot max safe integer. This will create a matrix that's full of very large numbers. I will say that our position, I will also use the point interface because I kind of understand that. So the position will be a point. And the matrix of the current point, or we can have 0, 0 because that's where we are, will be 0. So this matrix will have the prices of each cell, which means that for this cell where we're at, we're gonna say the price is 0, and for every other cell, the price is the maximum possible value. So now we're gonna have a loop. We're gonna have a queue, and that queue will have a position, and as often we will have the following loop. While we have elements in the queue, I will rename this to start position. We will get a position of here, and since we know that the queue has things, we'll have that. So we are actually doing a recursion, but in a more ordered way. And this is more a breadth first search and not a depth first search with we get with classical recursion. And we will actually now try to find the prices for each of the elements. So we will say we have our position and we can have the price of that position. It's this much. So this means that we don't actually need that. We can go to each of its neighbors. We can go to each of its neighbors and see if their price will be bigger or smaller than the ones we get. So we can say we have the left, the down, the left and the right. We have all those positions and we can say, yeah, those will be the up price, the down price, the left price and the right price. And if the up price is bigger than our current price plus the input, so these will be the prices. These are the pet prices, or because we will have the total price, the minimum price that it takes to reach this position from the goal. Otherwise, we have that. And these are the separate prices. So, yeah, let's call them input for the original thing and prices for the prices. So, the up price is the current maximum minimum price of that thing. So the minimum price that we can pay and get to the up cell is that much. And we do have the current price, the price of the current cell. And then we can add the input of the up cell. So this price is what we can offer coming over from this side. Is it less than what we already have a way of paying? So basically this we're doing some kind of a price matching. So if, for example, we already know that for this cell we can get to that by paying 75. And now we're coming over from this side and we paid 70 to get there, which means that we can get to this cell by paying 74, which is less. And that means that now we are the best price possible. However, if we get to here by paying 85 and then we get to pay 89, we are not the best price. We don't need to entertain that option at all because we are looking for the minimum price. So we're saying if our price is less than the current maximum price, the current minimum price, then we're in business. We're gonna set, actually I will do it the other way around. Now it will be iffy because we will have lots of prices. This is the current price for up and this is the new price for up. So we're gonna set the current price for up. Yeah, we can do that. So up price, these are the prices that we can offer. Well, it's not gonna be up, it's gonna be down. And I'm gonna make a back invariantly. Left, right, right. And if we can say that the current price is less than the price that we can, is bigger than the price we can offer, then we can say, well, set the current price to the price that we can offer and say that we want to actually do that. We want to process now from that price. And note that at the very least, one of these, there is no just no way that all of these will be actually correct because we are coming from one of these directions. So at least for one of them, we will have something that says, well, I can offer you your price plus twice my price. And that's by definition bigger than your price. So we kind of do that. And this will run for a while. And after a while, we're gonna run out of places to go. So everywhere we try to go, it seems that it's cheap, it's more and more expensive. So we are not more cheaper than whichever we think we did. So that means that we will be done. But I will rewrite this a bit, reorganize it. So that we could separate processing for each of the sites. That's down, that's left, and that's right, because we are gonna be working with matrices and matrices have boundaries. So we only do this if y is bigger than 0. We don't need the second one because we'll do that. And why we didn't do this from the start, I don't understand, because now it's gonna be a bit iffy. And we're gonna need to have convenient checks here as well. If y is yeah is less than input length minus 1, because if y is input length minus 1, that means we're on the bottom row and we can go down. Now we have x0, and now we have x on the rightmost column. Not prices, but print matrix prices, and this will be a mess, so I will say for yeah, something like this, because the value will be actually a number. Come on, prices is not any, because we are filling it with that. Prices is a number array. Put them to a length of 3, length of 4. Let's have that and see what we get. So this is what happens if we ignore the go three only three parts in the same line. So you can see that the cheapest way to get to this is 3, the cheapest way to get to this is 4, 6, 9, and we usually won't have a situation, but here we have something like this. To get to this part is 73, but to get to this part is 67. And we had 246 calls. How many calls are we going to get on the huge example? That's a question that I might want to ask. And this approach is a kind of variant on the Dijkstra problem, but kind of adapted not to nodes, but to specifically matrices, because we're not investigating how many neighbors everybody has. We know that it has 4 neighbors, and we're consciously saying, yes, that you can backtrack, but you're never going to choose that because that's stupid. I didn't need to see these numbers, so I will run it again and not just go through it, because this is a how many by high money? 140 by 141 table. That's a weird number. Hopefully we won't have to separate it into some kind of subsection so that there are checkpoints, for example, that we must pass and things like that. It could be for part 2. I haven't seen part 2. So we have 107,000 calls, which is not a lot, to be honest. And it says that we can get, oh, it's 141. And in general, we will need to return prices of that much of the bottom right corner. So if we didn't have that situation when we had to basically only move up to 3 lines in a certain direction, the answer would be 774. So at the very least, we have a lower bound, because whatever our answer is, it's not going to be less than that. Also, in our case, when the answer is actually 102, yeah, we're gonna take that. However, there are some ways in which we can kind of optimize this. We can kind of make it better. We can kind of make it more focused, because right now we're calculating all the possible ways that we can get somewhere. And so we definitely run through a path that try to get all this way, then return all this way, then go all this way, and so on and so forth. We skipped on a lot of them because sometimes we said that, well, somebody said, well, I can get here in 15, and then we said, well, we can only offer you 70, and they said, thanks, but no thanks. But we have our algorithm functional with specific and ugly code with that. But now we're gonna have to have a direction. So I think that basically now we had a situation before where we could enter a cell from 4 different places, but we didn't really care about that. We didn't say that if you go left, don't go left, and things like that. We knew that that would be done. we actually kind of know the direction because we are going up or we're going down or we're going left or we are going right. So we can have some kind of a direction. And note that in this case, we don't kind of worry about the path. We're just interested in the minimum value. But now it seems that we have to take care from where we did enter and also what was the length of the straight line before that. So there are actually 12 ways to enter this. We can enter it from the left after starting moving left on this position, or from here, or from here, or from here, or from here. So we will have another interface that will say, well, direction. No direction, but travel type or something like that. Just call it travel. And that will have a direction, which is, I'm gonna be explicit, so it's up, down, right or left, and a distance that is actually, I'm gonna be strict with that, it's gonna 1 on 0, 1 or 2 or 3. And this is a type that actually has 12 different values. Or we can just use strings, but let's be explicit, there are 12. Yeah, I will have prices or price list. So in that price list, I will have a price for each cell for each combination. So if up 0 will be a number, up 1 will be a number, up 2, down 0, down 1, down 2, left 0, left 1, left 2. We have these 12 numbers instead of that. We might use this, but we might not. We don't really need them. And I will just then make const get default price list. It has no parameters and it will return yes, this. Because then we can say, instead of filling it with that, we can fill it with, oh no, this won't work. Fill is always taking a single context. We need to map it from that to get default price list. And this actually is not a number array. It's a price list array. So one of the conditions of the task is that we can actually go back to the starting position, which means that we can go this way and this way. So we can go from 2 to 4 to 2 to 3 to 2 again. But I don't see how we would get anything by coming back here because at the very worst we cannot continue going straight, so we're not gonna get bonus, we're not getting a speed up bonus or something like that. So I'm quite confident that we won't have loops in this solution because a loop doesn't make sense. We can just not do the loop, basically ignore the whole loop. And that's a good thing because that will cut on some of the paths we have, but there will still be a lot of them. So we can just say that our zero cell has generate them these prices. Now I will want to have 0 across the board. Will you be able to generate it now? Come on, generate it all at once. This is gonna be very hard to retype if I see that this is actually a very bad situation. So, and we also want to have our direction or our travel type. So the start position is no longer a point. This is a point and a travel type. So our start position actually won't be this, but it will be direction we're moving to the right, and the distance that we already traveled to the right is 0. I think. Because technically we can move this. Oh, so we're gonna have to invent one more type of direction. That's the start. Because there's actually nothing stopping us going 413 because then means that we only moved 3 times in that direction. So now we have our queue that's filled with the stand position, and we can get the price for this, and we want to do some more checks. So this says, what happens if we go up? Well, the up price let's see what will be the new up price. It will be the current price we're getting the prices for our current position. This is gonna be tough to actually say it out loud because there are lots of lefts and rights and tops and whatnots. So yeah, we need the direction that we're moving in. Three to four. Yeah, if I was totally sure that the direction that we need won't include going in these three, I would totally. So if this was a 9, I would say, okay, we're not gonna go that way. but it's a 4, which is kind of the minimum from what I can see from these two. We might go this way, and then this way. Okay, we can just say that we're -1, so if we go right once, we're gonna get to 0. So now I'll actually say that this is a number. We will do it programmatically so that we don't get to that. So now we are in our start position. We have a current price of how many. We actually have a current price because we did spend some amount of lava to get to that specific start position. And that price, yeah, we actually got it before from here, but we can say we can add a price as well. Let's add it to the traveling point. This is the price so far. So instead of using XY, we're gonna have the direction as well, the distance, and the price. Which means we don't need that line. And if we want to go up, the price for new up price will be the current price plus what we have to pay to actually go up. But can we go up first? So if direction is equal to up and the distance is equal to 2, we can just ignore this direction. But we cannot call continue because we want to do all of those. What we can do the magic of functions. Next, positions. That's an array of traveling points, and I will have this done. So get left position. Yeah, we can have something like this. We don't actually need next positions. And let's create a method for that. So now we can say if y is less than or equal to 0, return null. Yep. If direction is up, and we already get two distances. No, we already got two distances. Actually, I will do it this way. If the direction is up and we continue going up, if the distance is 2, return now. We cannot. Otherwise, return that we're going up, and we're increasing the distance, and the price is the new price. So we're gonna that's the current price plus you might need the input as well, because that's the prices, and all this doesn't help us too much, so we might want to do this. We want to have the prices, which is the the input, we're gonna need to have, we're forgetting something. We're gonna need to have the prices as well here. So these are costs, and these are the prices, which are price list array. Price list matrix, and then we have a position, which is a traveling point. So we need all of this. So position dot direction, if the position dot distance is that, then we have an object like this, and we don't just need to return it. And that's not position, that's an, let's call it L position. This is not an L position. What am I doing? This is an up position. We would have been so messed up. Was Ethion. This is gonna be an object that has position.x that will have y as position.y -1, which will have the direction of up, which will have a distance of, again, not L position, U position, up position, which will have the position dot distance +1. And right now I will say it will have the price of 0, because we don't want to do that. But we might want to do something else. The price key that we want to use will be this. So we're entering into that prices from this position. No. Yeah. +1. because that's the position that we're gonna live with. So that means when we came to the next position, from this perspective, we had this price. So the next price would be position dot price plus the costs of y minus 1 x. This would be the next price. If the next price is bigger or equal to the prices of price key, yeah, this thing, come on. Yeah, price key we can say we're gonna need to do a lot of typing, and I will do it maybe later. And this says, no, I don't want to do that. But can we say that say it like this? Yeah, now this works. So it's not perfect. Actually, it's quite awful. But we can say if the current price is less than the next price, then we can just say, nah, we're not gonna do it. So now we have three scenarios where we cannot go up. One is we cannot go up because there's nowhere to go. The other one, we are too wonky or whatever to go up. And the third one, it would be more expensive. Somebody already went up with the exact same position and it was cheaper. For example, if we have something like, yeah, those dots and whatnots, we can have going it this way. Let's do 1, 1, 1, 1, X, and get one price. Or we can say, so now we are going, or do it like this. So we came to the X going up for the second time. Yeah, that's valid, but we might have gotten to it like this, 2, 2, 2, and now we went to this thing going up for the first time. No, that's not gonna do it because that's different, but we could have gone like this, 2, 2, 2, 2. So one of these will have a lower price than the other, and we will say, well, that is the lowest one. So we will run all the possibilities until we get to, we will have different waves. So this might include moving a bit more through the maze, but I kind of hope that it will work. So right now we have a solution for what the price will be here. It will be the next price that we have. And here is the part that I won't like, is that will actually need to set this value. So the prices, each time we call this method, the prices will actually get mutated. But this is only if we're going up. So we are getting the up position and we already have an up direction. However, any other direction, Actually, not any. If we had, this is relatively simple. If position dot direction is down, which means we went down, we can just say, no, don't go up. You just came from there. You cannot backtrack. It's also more expensive, but if it's left, then we don't need to do all the other checks. We don't care what the position is. We don't care about anything. We're gonna need to do some things like this. So this means we came from the left, no, going left, and we're turning up. That is always legal. So our position will be literally up 0 because this is this case 1111 x. So we're from here and we're going up. Our direction was previously going, no, we have the other left or something like. And now we're going up. So the key under which we will come is up 0. So the next price will be the cost of, that's the next price. This is the current price that we have. If the current price is bigger, then we return null. Otherwise, the U position. Oh, and here we can just say return U position. And now we will need to write 4 of these methods. I think I might be overdoing something. Actually, we don't need this. It doesn't matter if we came from the right or the left. The next price key is that much, the next price is that much, the current price that we had is this much, and now that's the position, we're going up, the distance is 0, and U position. So now I will make another 50 line monstrosity to have the get the down position. So here we will have if position of y is bigger than or equal to costs length minus 1, then we're going to return null. So if the direction is down and our distance is 2, we're going that way. Otherwise, it's down with the next. So it's y plus 1 and it's y plus 1. And that is the same. And this is plus 1 and we're going down and the distance is increasing and the price is the next price and the prices of this should be that and return the position. Yeah, this helps us because it's not down now, it's up. Otherwise the price key is down 0 plus 1 plus 1 return null plus 1 direction is down, that's 0, that's, and once more plus 1. I will have some bugs. Hopefully that works. So why is it? it says this cannot be a traveling point. Actually, it can if we say that we are using it as a constant. Because then it says, oh, which means you're not going to change the direction. Because if I don't do that, this means that right now I can say start position dot direction equals whatever I want. But now it says, no, you said it's going to be a constant, so you're not going to change what you're going to do. So, yes, now it says, I know that that is right, and if that is right, that means it's a traveling point. It matches the traveling point. And I can say, now, if left position is a thing, if it's not null, we're going to push it to the next positions. Because, and this thing has the same problem again. But now I will just say this actually returns a traveling point, and this actually returns a traveling point, and since the method is written in such a way, or a null, yeah, it says it's okay, and I will have to use the const here as well. Okay, so this is a traveling point or null, and this is a constant, and this is a constant. Do we need to change it in two places here as well? Yep. Oh, plenty of lines of code, and most of them deal with plus ones and minus ones. And now I totally hope that this will take on. Do it. No. The position to the left. So yeah. Yep. Yep. If it's right, otherwise it's left 0. It's either correct or not, but nobody knows. So this is actually up position, and this is actually down position, and this is actually left position, and I think I have a problem here. And now we're gonna have the right position, up, down, left position, right position. And I don't even need this. I can just say if we have an up position, q.push up position. What's the problem? The problem was that the queue only saw a start position, which was a constant, and says, I guess I'm only getting start positions. So I have no idea what I'm doing, but I have an idea that I might run it this way. I know that the format is correct, but I have no confidence in what I wrote inside of the format. Only, yeah, this is easy because what we're returning is something like that. I will just return -1 here and maybe here, and I will just console log the prices of that because that's now a full on object. So this should return the last prices of the last cell. And note that some of them will still be max value because we don't really have a situation when for this number something keeps going up. I hope it doesn't. But in effect, we're investigating all the possible legal moves that we have. And this is not something I believe that we should be able to get. That we're reading a price key that just doesn't exist. Reading down 0. Yeah, because this is undefined. So we either messed up on the very start or we messed up somewhere further along. So this is our input. So this is our input. So from 2 we can go to 4 and 3. So we have our position. Since we're going right with a distance of -1, get the up position. Did we manage that? The up position is null. Yeah, we cannot go up. Get the down position. This should give us something, and it gave us a exception. So let's see what the prices are actually. And that will be better if I actually run the 17th day. What are the prices? Exactly, especially what are the prices of 0? Where did I use fill where I shouldn't have used fill? It's the other way around. If you're gonna use map, you're gonna have to use fill first because otherwise the array constructor is totally weird and it just creates an array, but it doesn't create a place for you to put your elements. So since it doesn't have any elements, it doesn't actually create anything. So 1 back down. Let's see how many more do we have. And we're already 1 hour in. So we'll see if we get anything. Oh, this actually looks correct. So we didn't manage to get to the from the up or from the left, but we were able to came from the down. Yeah, going down, and we were able to get to it going right. And the minimum one is this thing. And instead of the other code running 246 times, this ran about 100 times more. which is to be expected. So now I think that we can say we can just get those prices. That's the finish prices are those, and those are prices of that thing. And then we can say, yeah, get all the values of the finished prices and give me the minimum price and return it. So this should give me 102 as the response, because that's the minimum wave that we were able to get to it. And it did it surprisingly fast. Let's see if the same thing happens here. I'm not too confident that we will get an error so fast, but I will say on every million calls, 100,000. Now let's go with a million. Or just add, and the Q is that much. So every million calls we're going to get a diagnostic message out. This can be very important because we want to see that it's actually running. A few seconds passed, we didn't do anything. So now we're gonna go the other way around. We're gonna say print something every 10,000. Yeah, this is something. So the Q is gonna go up and up and up and up. And then it's gonna start to go down eventually. And then we will finish. I would expect to have, we had about 100,000, so that means 100, about 10 million calls, so this will take for a while. So after an hour of running, we are at somewhere around 5.5 million calls, and the queue is about 800,000 items long. But we might have a problem with that, because even in the huge input, we have 141 times 141 items, because that's the whole width. And even if we have 12 different ways to do that, that means the queue should never be more than this number big. But since it became that, that means that we are actually queuing up a lot of duplicates. We are entering the same cell from the same direction, maybe with a different price. But if we compare those different prices, we can see that one is markedly worse than the others, which means that we will need to constantly trim our queue to get to this number. And since we're gonna do a little bit of queue management, we will do a bit of more work with that, but all of that will be waiting for you in part